G'day viewers. In this segment we'll learn about the User Datagram Protocol, or UDP. UDP provides the datagram service at the socket layer. And as I've said before, it's really a glorified layer on top of IP, which really allows packets or datagrams to be delivered. So in this segment we'll learn the ins and outs of what's behind UDP, and the answer is really not a lot more than IP itself. Okay, so UDP as a datagram protocol, an unreliable one at that, it's used by applications that either don't want reliability or that don't want some other kind of abstraction than messages, such as a byte stream. So there are several examples here. One example is a voice over IP application. Typically for real-time conferencing, we don't want reliability there, so UDP is a good fit. Other kinds of protocols that might use messages would be the DNS and RPC, which stands for Remote Procedure Call. We haven't actually seen the DNS yet, we'll see it later, but it's the machinery that maps between host names like www.uw.edu and addresses, IP addresses. And maybe a third class would even be bootstrapping protocols such as DHCP. Since these are used to get the network going, it's easier in some sense if they don't rely on all of the complex machinery of TCP. By the way, you can see from this list and reasoning that if an application wants both reliability and messages, then it has work to do. UDP gives you unreliable messages, TCP gives you a reliable byte stream. Reliable messages fall somewhat in between. So for instance, protocols that want that, like the DNS, must provide the reliability themselves as part of the application level protocol. So in that sense, the internet protocols, TCP and UDP, aren't a good fit to all applications. Okay, so we can see how datagrams are used at the socket layer. Let's see. Here is a simple time sequence diagram. We have a client and a server. The client is sending a request to the server who's returning a reply. The socket calls we would make to cause this to happen would be, first of all, we would need a socket on both sides. Now, on the server side, we'd need to bind that socket to an address, a well-known port, so that the client could contact. So we now simply want to send a datagram. What do we need to do? Well, usually the server will call receive, in this case receive from, to receive a message. That's a blocking call, so that really says I want to receive a message, and the process then blocks while the kernel waits for a message to come along. At some later time, the client will call send to send the request from the client to the server. At this stage, the receive from call will unblock and we'll have the information there, and the server can then process the request. On the client side, right after sending to, since we'll be expecting a reply, we'll call receive from. This instructs the client now to wait for a message. And after the server has finished processing the request, it will send. It will send that reply using send to. And then the receive from call will be unblocked. The reply will be received by the client and the client will process it. And then at some later time, when everyone's done, they'll call close to tidy up. So those are the sequence of socket calls which is used with datagram sockets for a very simple client-server exchange. I've cleaned it up here on this figure, and you might note that I've just starred the calls which block, which sort of explains how the flow of programs. Okay, so that's how you'd use a datagram socket. We did see examples of using sockets previously a long time ago in the course, but they were for stream sockets, so the datagram sockets are slightly different. No connections and slightly different forms of receive and send. We can also look at what's going on at the host while we make all of these calls. This picture here shows the buffering that happens inside the transport layer. We have the application layer at top, so this is all of the app processes which are running. They use the sockets and ports to interface to the transport layer. And at the bottom of this picture we have packets, and they're going out the physical network, so I'll just draw a wire. Now there's buffering inside the transport layer. When an app calls, when segments come in from a transport peer on the other side, they're placed in these buffers inside the kernel. You can see that for some sockets there are many different segments sitting here in the buffer. They're going to wait there until the app calls receive, at which time they'll be pulled from the kernel and handed up to the application. Similarly, an application might have data to send. And when it does it, if it calls send to, that data goes down to the kernel where it sits in a buffer temporarily. An application might send more quickly than that information could be put on the local network Y, in which case there'd be a little bit of temporary buffering inside the kernel. But as you can see here, the setup is fairly simple. We just have that buffer as a staging point between the send and receive operations. Down the bottom here, this block saying port mux demux is simply the multiplexer and demultiplexer, which is using the port information when you get a segment in to assign it to the right queue, and vice versa, taking segments from all of those queues and sending them out into the network. Well, there's not too much more we can look at for UDP. I can show you the header. You'll see the header is actually very simple. It's pictured here. It has the ports, those 16-bit ports, which identify the sending and receiving application processes. It has a length field. You can send datagrams of up to 64 kilobytes in length. There's also a checksum, a 16-bit internet checksum, just for a little bit of added reliability. But this is pretty much IP. There's only one other thing I can think of to tell you, and that's a little bit about the checksum. The checksum here, well, first of all, it's optional, but second, it covers not only the UDP segment, but it also covers the IP addresses that are passed down with the UDP segment to the data layer. And these are checksum by placing them in the form of what's called an IP pseudo header. You can see it pictured below here, the source addresses and a little bit of information. The checksum covers this block prepended to the UDP segment. It's a little unusual that we would have these source addresses here inside the transport layer. It almost sounds like a layer violation. It's not quite, because these are parameters that the UDP layer knows and is passing down. The UDP as a transport layer protocol is passing down to the network layer to tell it where to send things. But it does show you some of the linkage between layers that we often conveniently ignore. And a final trick is that a value of 0 in the checksum means there is no checksum. That's how it's optional. With a quirk of our ones complement checksum, there are two different values for 0. So if the checksum comes out to really be 0, we can send it in the form of all ones. That's an equivalent value for 0, rather than all bit 0, which will indicate there's no checksum. That's it. That's UDP.